I am going to
16 iterations.
iterations.
It's a mathematical process that does iterations. So and the more iterations you do, typically the worse the artifacts become. But notice the use of the word typically. You have to play with this stuff to really decide what you want to do. Like Mark quoted even numbers. I've found numbers like 13 usually work better.
Yeah.
Pays your money and you takes your choice.
Okay, Mark, I'll let you pick it up.
Okay, let me see if I can actually share the correct screen since I have two screens active. All right. Oh, great. Hold on. Duh. Okay, forgive me if I get this wrong the first time. That's the screen I want to share. Okay, you should all be seeing the
We see
guest view. Pardon?
Yeah,
flats
perfect.
where needed.
Okay, so you're not seeing PowerPoint. You're actually seeing the presentation itself.
Correct.
That's
Okay,
correct.
thank you. Okay, great. Okay, here we go. Let me move you guys over so you're not on my screen. Okay. Okay, why would you do flats? Well, I think you might have got a flavor from Mark of why you want to do them, but I'll describe it. By the way, by way of disclosure, I almost never do flats. But that's because the way I approach imaging, I definitely try to avoid them for a whole bunch of reasons. Not that they're bad, I just try to avoid them because in my situation where I image and the way I image, it would be very painful to do them. But there are times when you have to. So let me clarify that. So what are flats for? Well, they're used to fix non-uniformity artifacts in images. You know, like somebody's hair is on the sensor, and I'll actually show you an example of that. Or there's some dust in the optics at a bad place, as opposed to a place that doesn't matter. Or there's a bottleneck in the optics that creates vignetting, where the corners get dark, as Mark illustrated in that picture of the Cone Nebula. So there's different kinds of non-uniformity artifacts. They have different causes. They have different ways of reducing their effects. And in some cases, the best way to reduce them is with flats, but not in all cases. Okay, so again, as Mark said in several points in his presentation, some of this stuff is experience-based and you develop techniques that work for you and the way you image. I have a very restricted part of the sky I can get to, so I can't be shooting, 16, for 3 hours or something. Okay, so this is an example, and I hope you can see it. This is an example of a dust particle that's right on the sensor. So can you see it? It's a black little dot inside that red circle.
Yes.
Yeah, we can
Okay. So this, by the way, when Arlene and I go on vacations and we take pictures and she produces her videos, I have to go through my pictures and I have to periodically go through and individually pick out those bad spots in the, when we're, from a daylight scene in Mallorca, Spain, because this can happen with a regular camera, particularly if you change the lenses, because dust can get in the camera every time you change the lenses from a wide angle to a telephoto to something else. This can happen with regular photography too. So that's an example of a dark speck that's right on the sensor, actually. This is an example of a piece of dust that's on the rear element of a camera lens that's very close to the sensor. And this is a higher particle that's actually lying on the sensor. I mean, that stuff, this is a normal camera lens. This is a normal, in fact, it happened to be a Nikon DSLR. I've lost my pointer here. Hold on. Okay. So the solution to those kind of problems with a camera, whether it's DSLR or CCD, is you clean the sensor. And they make these things called loops, which is this little gadget here, which has a magnifying glass. It has LEDs in this little ring, and you can look down into your camera and there's this little U-shaped bracket, and you can reach into there and clean the sensor. And they make special lens cleaning kits for DSLRs. Now, the things to observe about this, and I typically have to do this a couple of times when Arlene and I are traveling. I have to do this a couple of times a trip because I'm changing the lenses in the middle of a desert, you know, in Petra, Jordan, and some dust gets in the camera. Okay, well, I'll fix those later, but I want to get rid of those the night for the next day's photography. And the same thing's true with astronomy. So I'm going into the DSLR here, and they make little cleaning kits that you can go in there and clean those sensors with. And I use the same loop, the same camera loop to go in and clean my CCD periodically. Now, the effect of the dust and the location matters a lot, along with the way the optics are laid out. For example, if you have dust right on the surface of a sensor, the sensor, of course, has the pixels in it, and it has a cover glass that's right on the sensor. Now, in the case of DSLRs, by the way, that's the thing people often remove because it filters out the red, hydrogen alpha. But that's a different issue. But this piece of glass is right on top of the sensor. It protects it. And if you get a piece of dust on the cover glass, it's going to form a dark speck, period. The only way to get rid of it is clean it. You can image process it out later, but frankly, you ought to just clean the bloody thing, because the less problems there are going into the image capture, the less problems you'll have. So that kind of thing, doesn't matter what you're dealing with, what technology, the best solution is to clean the bloody thing. Now, if you have an optical path and you have if you have a filter in front, say it's 10 millimeters away. Now in my camera, that is just a cover glass to protect it, because the sensor is cooled thermoelectrically, the sensor is cooled, so they don't want frost to form on the sensor, so they put a window in front of it. Well, what happens if I get some dust on the window? Well, that dust on the window obscures a small part of the optical path. Now, the angle of this optical path was chosen to represent something like an f3 lens or telescope. And so this dust particle obscures a very tiny part of the optical path. So it is very unlikely to cause a problem. Only if I stretch the image and get really greedy might I see the effect of that. But if I'm shooting at f6, which has a narrower optical path, the telescope is up at the top shooting down into the lens is up at the top shooting down into the camera, then a tiny little dot obscures a sizable fraction, like in this case, probably 25% or more of the optical path. So it's going to create what's called a dust donut. And that's because this thing's only 10 millimeters away. Remember in the first picture I showed, there was this big fuzzy spot over at the right. That was caused by a fairly large piece of dust on the back element of a camera lens that was very close to the sensor. So if you move the dust further away from the sensor, it's not a problem. But if the dust is close to the sensor, like right on top of this cover glass on the sensor itself, it's going to create a dark spot. If it's further away and your optical path is narrower, then it's likely to create what's called a dust donut. So the moral here is, the slower the optical system, the more vulnerable it is. Now, you may have no choice. You may want to shoot something at f6. So you got to deal with it somehow. Either clean this filter or this cover or this window on your camera. Now, in the case of a DSLR, this is the back element of the camera lens, which, depending on the lens, may be 20 millimeters away, maybe 30 millimeters away, maybe 10 millimeters away. Depends on the lens. In the case of a CCD that's cooled, this is of the order of 10 millimeters, because they don't want you to generate frost on top of your sensor. Now, here's an example from the professional world. This is from the Cassini Saturn mission, unprocessed. If you want to go see the original, go Google on Attack of the Dust Donuts. This is actually a result of dirt that's on the filters in the Cassini telescopes and cameras. Now, it was made worse by the fact that the lighting conditions were very dim and they stretched the image, which made the dust donuts look worse. So it's another case of, if you get greedy, you have a penalty to pay. Now, you may have no choice. You may have to get greedy because the object's dim. But in this case, it was just the lighting conditions.
I see diffraction rings too.
They look like diffraction rings. Yeah, this must have been, it's very hard to find detailed information on this stuff, unfortunately. And JPL and NASA assumes everybody is an idiot. So it's very hard to find out what the focal ratio was of this optical system. But my guess is it was pretty high. It's probably well over f10, but that's just a guess. So, and there may have even been some interference effects inside the filter layers. I mean, I don't know. Again, it's very hard to find. Now, in the case of Cassini, remember, they can't go clean their sensors. They can't go clean their filters. You know, they're 90 astronomical units away from Earth, so they can't clean their stuff. So they've got to either take it out with an internal target to do flats, or they've got to take it out with software, or they've just not got to get greedy. Interestingly enough, if you go to the Sloth website, if you go to this article on Attack of the Dust Donuts, you'll actually find that there's a link to an add-on to PixInsight, which is one of the one of the newer imaging process programs that Mark mentioned, that actually has software tools to remove some of these things. I've not used them myself, by the way, but PixInsight is very popular with a lot of imagers. It's $250 for a lifetime license. Okay, so that's the dust donuts, and that's the dust artifacts that are in the near field. Then there's the real fundamental question of non-uniformity of the pixels of the camera itself. When cameras are produced, whether they're astronomical CCDs or DSLRs, the manufacturers calibrate the response of the pixels to produce a uniform response. Now, as cameras age, that information may become irrelevant. In extreme cases, the pixels may die and become what are known as dead pixels, or they could be turned on permanently, in which case they're called hot pixels. Dark frames tend to take out the hot pixels. The dead pixels, you either have to correct the pixels in software or let the camera do it. A lot of DSLRs have what they call a pixel mapping function that handles the dead and hot pixels. If you don't have that function, you may need to use flats to get rid of that. Darks and flats in combination will get rid of this if it's a problem. If it's not a problem, you don't need to do all that. Finally, there's obstruction in the optical path, which is also known as vignetting. Now, Mark illustrated some examples of that. You could see, for example, in his cone nebula shot. It always gets worse at the corners, and I'll describe why. It also gets worse when we get greedy and stretch the data. Now, sometimes we have no choice. We have to stretch the data. It also happens very often usually when the sensor is larger than the bottleneck in the optical path. And of course, the diameter of the bottleneck, the size of the bottleneck, and where it is in the optical path both matter. And flats can compensate for a moderate amount of vignetting. The reason I say moderate is at some point, if the vignetting is 100% at the corners, the signal to noise ratio is bonkers and it can't really be accurate in that case. But for moderate amounts of vignetting, it can do a lot for you. And frankly, if I were to use flats, that would be the reason I'd use them, because of the way I image. And basically what the idea is, the flat is used to scale the pixel response to be a uniform thing, to be uniform across the entire image. To illustrate the point, and again, this is not a function of the camera, this is not a function of dust, this is a function of the optics of the telescope or lens and how it relates to the sensor. So here's an example. The main optics is illustrated just as a simple refractor. If it was a reflector, you'd reverse the whole thing. You'd flip it over 180 degrees. So the main optic collects light and all of it's delivered to the center of the sensor. So this is the sensor plane, this is the corners, this is the center. So if you're right on axis, everything's delivered. Yeah, okay, if it was Newtonian, there'd be a diagonal obstruction, but that would be constant anyways. So now we suppose we have a baffle, like you have in your Schmidt-Casses, or a secondary that may be too small, or we have an intermediate optic, like a correcting lens, or a field flattener, or something like they have in the Edge HD optics, or you have the second element in a conventional camera lens, or third element, or fourth element group. And so suppose the stop It could be just a baffle or a stop in a conventional refractor. So if it's too small, it doesn't matter for the center because it's always going to get through. Nobody would sell a telescope with a baffle so small that it didn't let the whole main telescope go through, the main objective. But off axis, it's a different story. So if the object is off axis, if it would appear in the corner, in this case, whole sections of light would be cut off. This dotted line here wouldn't get through because it's obstructed by the baffle or by the small size of this intermediate optic. And that's what causes the vignetting at the corners, basically. And so the rays at the bottom or the corner are cut off because the stop or the baffle are too small. And the net effect is you have 100% illumination here, and you may have 80%, 50%, 70% illumination of the corners. And this is avoidable by proper matching of the optics to the sensor, which, of course, if it's a big sensor, costs a lot of money. And the thing to remember is the constriction may be in front of or behind the main optic. In the case of Newtonians, there's two places where the constriction can occur, for example. In the case of a Newtonian, it could be the inner diameter of the telescope tube at the very front, or it can be the size of the diagonal mirror. Very commonly, telescopes are sold with diagonal mirrors that are too small for their back focus. That's a function of that. And this is very commonly a problem if you have an 1.25" focuser or small filters and an APS-C size sensor, which basically has a 30mm diagonal. It can also be a problem with a 2-inch focuser and 2-inch and full frame sensors. If you look at some of the larger imaging telescopes, they actually have 2.5 or 3.3-inch focusers. And the reason for that is to avoid vignetting with large sensors, whether it's a full frame DSLR or a 40mm square CCD. The problem is once you go beyond 2-inch focuser barrels, corrective optics, field flatteners, whatever, become horrifically expensive. It's like the situation with DSLRs that were based on 35mm formats versus Hasselblad 120 formats, which are a totally different world. Just add a zero to the price of everything. So what to do to avoid needing to do flats? And by the way, you can't always avoid them. If you need them, you need them. First of all, watch out for the focuser optics and sensor size problems. And if it's only a problem, just crop a little bit and be happy, assuming your target allows it. If possible, clean and seal the near field optical path. This is reinforcing some of what Mark said. He talked about how he has his standard setup and he keeps it that way. And that's what I do too. Now, that is very hard to do with LRGB and filter wheels, particularly if you have to set up and tear down every night. So this becomes a question of how you practice and what your procedure is and what your life allows you to do. So if possible, you clean and seal your near field optical path. For example, the way I normally image is with a CCD single shot color camera with a chroma corrector on it. This is all empty space. So all I have to do to keep this baby clean is clean the window on the front of the camera that's used to keep frost off the sensor. Then I blow everything clean, screw this down, and I don't touch it for months, assuming there's no dust donuts. I test it. If there's dust donuts, I clean it again. And then I leave it for months. If I have to change the optical configuration, then I have to go back and clean it. But that way I don't really have to worry about dust donuts. If there's filter dirt or scratches, it doesn't matter because it's so far from the sensor. That's a good almost, 4 inches. So it's so far from the sensor, it's not going to make a dust donut. If I had dust inside 10 millimeters away from the sensor, I'd have a problem. So the way I happen to work is, not everybody works the same way. That's a thing to remember in all this. You've got to develop procedures that work for you. The way I work normally, I don't care about flats. I have a little bit of vignetting because when Orion designed this thing, they used a T-thread for the connection to the camera, which creates a bottleneck. It's just the way they engineered it. So if I'm willing to live with a little bit of vignetting or unnoticeable vignetting, I don't care. There are times when I do care.
That's your Orion camera that I've heard about?
Yeah, it's the old single shot color. I mean, there are similar models made today by ZWO and other people. I keep hoping this thing will break so I'll have an excuse to buy a new one, but it keeps working.
That's the size of Arnold Schwarzenegger. I thought it was a lot smaller.
Oh no, this is really old school. I mean, the reason for the size actually is is the dissipation of the thermal load.
I got it.
Cool. By the way, for those of you who don't know, the devices they use to cool these cameras are about $5, and they're used in beer coolers for recreational vehicles. They're not some exotic technology. They're just not normally used in cameras. I mean, DSLRs, you're shooting 1/10 or 100th of a second exposure out in the countryside or whatever. You don't care about cooling. You don't care about thermal noise. With this stuff, you do. So it's really very useful if you're shooting dim images. If you're shooting bright stuff like the conjunction of the planets or a comet Neowise, you don't worry about cooling because they're so bloody bright. If you're going after dim stuff, you want to reduce that thermal noise that Mark talked about, and that's what the cooling's for.
Yeah, because you have very small, very weak signal, let's say, from a nebula, right?
Yeah.
And so you have to overcome the noise in some way. So some of it's cooling, some of it's dark frames. Yeah.
Well, the electrical noise, that's what the bias frames are for, is the electrical readout noise. Yeah. So, I mean, with this rig, I have a little bit of the corners get vignetted, and it's all Orion's fault for using a T-thread for this. Now, the reason they did that is so people could attach it with devices that were designed for camera lenses, blah, blah, blah. But if you were engineering this from scratch, you would use a 2-inch, M48 thread device. So you wouldn't have that 42 millimeter bottleneck. You'd have 48 millimeters of clear aperture. So when I look down into this camera, I can actually see where the body of the camera slightly obstructs the far corners. Hey, we live in an imperfect world. If you want perfection, just add a 0 to anything. By the way, I keep this thing in a box with a air seal, and I keep it stored with silica gel packs that I can dry out, so I don't have to worry about moisture getting into this thing. A lot of cameras nowadays, that's an old camera. A lot of cameras nowadays have a little plug in them that has a silica gel in it to keep the humidity out. Okay, so that's my particular approach. Now, when I'm shooting with a DSLR, I'll typically clean, and I'm really worried about dirt, I'll typically clean the sensor before I put the lens on. And that's what I did with Comet Neowise with my trusty 85 millimeter lens that I shot with a DSLR. And of course, consider image processing techniques. I referenced, if you go to that sloth.com website and look for their post-processing that has software that'll take out dust donuts and some of these artifacts, you might find it interesting. It does require you buy PixInsight, which is $250. But at least they're not going to charge you $250 next year. It's not like Adobe. Okay, so if you do flats, and I'm going to reinforce, I hope, some of what Mark said, the system has got to be set up in the same way for imaging as for the flats. Because if you change the camera orientation, the dust donuts are in the wrong place. The vignetting might be wrong. So it's very important to do that. And it's part of the reason I don't do flats, because I always set up and tear down, and I use Newtonians. If I was using camera lenses or a refractor or something like a system like Mark's using, where he doesn't have to potentially tweak the mirror alignments every night, I would probably do more flats. I do them sometimes. I use an electroluminescent panel bought on eBay, and I'll put it over a camera lens and do flats with camera lenses, because my camera lenses may have some vignetting. I keep things clean enough. I don't normally worry about dust, but it can be a problem. There's times you can't get away from it. And of course, you have to do flats for each filter wheel separately. And if you really think flats are essential, from my perspective, while the t-shirt trick works, a lot of people use things like like this, which was, again, this isn't big enough for a big telescope, but for a small telescope or for a camera lens, this is fine. These are like $10 on eBay, or at least they were.
And then, Mark, I have this one, which I found at American Science and Surplus.
Uh-huh.
So this is collapsible. I think they use it for like product, and there's all different sizes.
Yeah.
It comes with a control, and here's the LED light there. You can see. So I use this where I put the camera lens through here, and there's another insert to make the field flash. So actually, I put the T-shirt over and use this for the light. So it's because
cool.
Then the light is very uniform.
Yeah, and what's nice about that is you don't have to do that at night.
No.
You can do it, if you can keep the configuration stable, which is kind of hard for me because of the way I image, but there are times when I do it because I can keep the configuration stable. If you want to make your own light box, you can go on eBay and you can buy these LED strip lights that run off 12 volts. And when you get done with your project, you can put them under your kitchen counter.
Well, DSLR with the telephoto lens or any lens, that's easy to do the next day. Just don't take it apart.
Yeah, and that's typically where I'll do it when I need to do it. I try.
Right.
I'll be honest with you. I try to avoid a lot of this stuff just to keep it simple. But if I need to do it, I do it.
Right.
So here's an example where I didn't need to do it. I used a library of darks because I'll typically go through every few months and shoot a new set of darks, and then I'll just use them for the next 3-4 months. The reason I do that is because the sensor does age, and there are dead pixel problems, and there are other things that happen. So I actually have dark libraries going back to 2010, but I normally use the ones that are most current, depending on the temperature, the ambient temperatures. There were no flats used on this because the optical path was clean. I described it that way. Because I could get away with this because I used the single shot color camera I just showed, and it was sealed at the far field. And I had cleaned everything in between. And I didn't have to crack it open. So I didn't have to worry about dust donuts or any of that stuff. And I didn't have to worry about vignetting because to get a big enough picture of because this is a fairly large chip camera, to get a reasonable image of the galaxy, I had to crop to 60% anyway, so the corners were blown away. So if you're willing to blow your corners away, depending on the subject matter and your focal length of your telescope, you don't need to worry about vignetting unless it's really severe, in which case you have no choice. Now here's one where I probably should have used flats. Again, I use the library darks, no flats. This was taken back in November. I was actually adjusting somebody else's telescope that I had hypertuned. And I had to do a lot of stretching because even with a dual band filter, the Sol Nebula is really dim. But it's only 80 minutes of image capture time because I'm using single shot color. But if you look carefully, critically, you can actually see the vignetting in the corners. So this is an example where if I really wanted to be professional about this, I should have used flats. It's acceptable the way it is. I can live with it. The reason I couldn't crop it, of course, is because even at 400 millimeters, this puppy's huge. So if I were to crop it to crop out the little bit of vignetting at the corners, I'm drawing where I would probably crop it to get rid of the vignetting. It would just be not formatted properly. 300 millimeters, same effect, I would have cropped it to get rid of the vignetting. But with this image, I probably should go back and reprocess it with flats to get rid of that little darkening in the corners. So, and with that, so to reinforce what Mark says, the way to reinforce and also to add a difference to what Mark said, I normally don't do dark biases. In fact, the Maxim DL Essentials tool I use doesn't even have bias frames. It just has darks and flats. I almost never use flats, and I'm happy with what I produce. Would it be better if I did more? Probably, but I have to weigh that against how I want to spend my time and what I'm trying to achieve. Now in Sequator, I've used flats and dark frames for some of those Comet Neowise pictures. I found that actually benefited the images to do the whole thing, do it using Sequator. So. Okay. Mark, I'll turn it over to you.
Okay,
You need to, I need to unshare or you need to
yeah,
unshare?
let's do the unshare thing.